We'll start with slide 1. Magnetic materials are crucial for the development of civilization. Magnetite was discovered a long time ago and converted into something useful called a compass. And I do believe the first discovery was somewhere in Greece, though unclear. And these Grecian people spoke Hebrew and asked the perennial question of why are these rocks different than all other rocks? And they are different than all other rocks. And this enabled the discovery of what's now called the New World, which is where I live. And so they're useful things to do that. Now, all materials respond to a magnetic field. They can either be repelled or attracted to the magnetic field. And they can be either weak or strong. So if they're repelled weakly, we call it diamagnetic. All unpaired electrons are paired up. And there's a slight movement depending on how you set up the experiment. But more importantly, if you have a superconductor, they can actually levitate items above it because they expel the magnetic field in what's called the Meissner effect. On the opposite side, as we know well, things are attracted to magnets. And this can be weakly, which are paramagnetic materials with some unpaired electrons. And there's some general response of attraction associated with that. But more importantly, we can stick things to refrigerators, and those are strongly magnetic and are ferromagnets in general. And those have lots of technological uses. Now, bear in mind that the Earth is a magnetic field. We have a magnetic field associated with the Earth, which is why a compass works. And that magnetic field, you can actually pull out your cell phone and check in the settings of it, and there's a magnetometer, and it will tell you that the magnetic field you're feeling is approximately 1/2 of 1 Gauss. And of course, that's very important to your survival on this planet because it attracts solar radiation to the north and south magnetic poles, which protects living things on this planet. But in general, we will talk about molecular compounds today and extended solids. And mostly molecular compounds, particularly organic compounds, are diamagnetic, in a few cases paramagnetic. And when you have transition metal compounds, they're typically paramagnetic, weakly attractive or weakly repulsive. And keep in mind, the greater the magnetic field, the greater the response. We won't spend much time on that today. So I'd like to just summarize a few types of magnetic ordering that can occur. Generally, if you have a paramagnetic compound, the spins do not interact with each other. But sometimes, and they will obey the Curie law, which is in green down here, where you decrease the temperature, the susceptibility will rise in accordance to the reciprocal. If there's a little ferromagnetic coupling, meaning adjacent spins are sort of associated in the same general alignment. Is there a question? I can't tell. Hello? Can you hear me?
Was just noise. Continue.
Oh, okay. There's a slight increase in the susceptibility, but if you lower the temperature so the thermal energy, kBT, is comparable to the magnetic energy, then in these spins that are aligned ferromagnetically or in that direction, lock into place, and you go into a second order phase transition to ferromagnetic ordering, as illustrated to the top right, where all the spins line in the same direction. The susceptibility will generally increase perhaps 6 orders of magnitude to this transition. And this is sometimes called the critical or Curie temperature with its temperature, transition temperature. Now keep in mind, ferromagnetically ordered materials have a lot of technological importance. Your cell phone, your camera, lots of things won't work without magnets in it. You can also have anti-ferromagnetic coupling, where adjacent spins are opposing each other in the general direction. And that leads to a decrease in the spin coupling with respect to non-coupling in green, the blue. And at an ordering temperature, then it will actually drop down towards 0 as opposed to going up to infinity. And we have aligned but opposing spins occurring in these cases. And that has a critical temperature as well for the second order phase transition. And sometimes that's called an AL temperature. Now, sometimes when they're anti-ferromagnetically coupled, the upspin is different in magnitude than the downspin. And that can also lead to ordering that looks like this down here, which is anti-ferromagnetic, but you can see the upspins are bigger than the downspins. And when they order, they actually order as a ferrimagnet, which means they order like a ferromagnet, but the spins are opposed to each other and the magnitude of the magnetization is not as great as if they all line in the same direction. And an example of a common ferrimagnet you're familiar with is in fact magnetite, lodestone, natural occurring mineral, which in fact is magnetic, magnetically orders, but it is technically a ferrimagnet, not a ferromagnet. You can also have a little more exotic phenomenon, and I'm going to bring up one example of it called a metamagnet. And here we have anti-ferromagnetic coupling, and we drop the temperature, or we actually put on a magnetic field. And when we put a field on it, the coupling increases so that the anti-ferromagnetic coupling, typically characterized by a coupling value that's negative, becomes ferromagnetic and becomes positive at a critical field. And when it goes to this critical field, you go from anti-ferromagnetic coupling to ferromagnetic coupling. And then when you drop the temperature, it locks into a ferromagnetic-like state, even though the ground state is an anti-ferromagnetically coupled state. And we call that a metamagnet. So in a metamagnet, we can get ferromagnetic-like ordering, but we have to put a magnetic field on it, and above that field, it acts as a ferromagnet. Keep in mind that ferro and ferrimagnets have magnetic domains. These where spins are macroscopically coupled in large regions. And illustrated on the left over here is several domains where the spins in those domains are aligned in the direction of the arrows. And these domains are fairly large, and they're typically hundreds of thousands of spins, almost 300,000 spins if it's iron metal, and 660,000 spins if it's magnetite. And they're fairly large in size, nanoscale, of tens of millions of cubic angstroms. And typically in a system, all the spins sum to 0 from the alignment, even though the regions have different rings. So if we look at the magnetization for this ensemble, and I only show you a 2-dimensional slab of a 3-dimensional phenomenon for simplicity, you can see that in 0 applied field, all the arrows sum to 0, and we have 0 magnetization. If we actually put a slight field on it in the upward direction in this case, we enhance the domains in the up direction at the expense of the domain in the sideways and down dimension, and we end up with a net magnetization in a small applied field. And if we increase the field more, the magnetization increases in that direction more at the expense of the other dimensions. And at some significant field, we can align all the domains in one direction, and we've reached the maximum amount of magnetization, which we call the saturation magnetization. And this is where all the domains align and coalesce to a large field. And you can see that this piece of magnetite over here has been aligned in a magnetic field, and it's strongly magnetic, and pieces of iron filings and nails will adhere to it because it's strongly magnetic at this point. Now, if you want to reverse the magnetic field from up to down, you have to flip this large magnetic domain. It does not go back into these smaller domains. And therefore, it takes a significant amount of energy to flip it. And so therefore, you will sweep out hysteresis loops where when you get back to zero magnetic field on the reverse, you have a so-called remnant magnetization, and you sweep out these hysteretic loops, which are characteristic and diagnostic of magnetic ordering and large magnetic domains. All ferro and ferrimagnets have hysteresis loops. Sometimes they're narrow enough that you can't easily see them. Sometimes they're very large. And this is an important phenomenon in magnetism, these domains. Now we're going to talk about molecular materials, molecules. And I think you should easily recognize that these domain size, which are necessary for magnetic ordering, are much bigger than a molecule. So molecules are very small. You don't have molecules or tens of millions of cubic angstroms with hundreds of thousands of spins. But we're going to talk about making molecules into magnets, magnetically ordered systems. And so ultimately they have to form domains that are large enough to give you this effect. But we're only going to deal with molecules. It's sort of like proteins. We have all these wonderful proteins in our body that are essential for our life, and we build them up from amino acids. And the sequence of the binding of these gives these macroscopic problems. So an amino acid connected together gives you primary, secondary, tertiary structures, and those are important biologically, but the building group is a small single amino acid. So we're going to take small molecules and build them up to large, important molecules. Now, the first magnet that's ever been made was made in 1600 approximately by William Gilbert, a physician in the Queen Elizabeth court. And he played physician and studied magnets. And he found out if you heat iron metal and you assist it by hitting it with a hammer and you cooled it in a magnetic field, north and south, even though he was English, he preferred writing in Latin. And so this north is the north magnetic pole, this is the south magnetic pole, and he synthesized the first man-made magnet. And the question we raised a few years ago is, can you make magnets using organic chemistry? Now, everybody in this audience here has played with and studied and has some interest in magnets, maybe scientifically or maybe just as a toy. But you think about your magnetic materials that you're dealing with, and you're dealing with probably iron metal, iron filings, maybe magnetite Fe3O4, maybe more sophisticated things like chromium dioxide, neodymium iron boride, any of these things. And the key feature of all these magnets is unpaired spins in D or F orbitals. And the question we wanted to raise is, can we make magnets with unpaired spins in P orbitals? And I've been told that that's not going to happen, but I don't listen to everybody. So the question now and the rest of the talk is making magnets with spins in p orbitals. So we are going to make and focus on organic-based magnets. We will define an organic-based magnet as a magnetically ordered material, ferro or ferrimagnet with a TC critical temperature, possessing unpaired electrons in a p orbital that contributes to the magnetization and magnetic coupling that controls the overall magnetic behavior. So that's what we call an organic-based magnet. Not a paramagnet, unpaired magnet spins, because that does not have a magnetic ordering temperature, does not exhibit hysteresis. Now, what's the advantages of an organic-based magnet? Is that we can modulate the property using organic synthetic chemistry, combine properties, improve the processing and fabrication, non-energy intensive. If you want to make magnets based on neodymium iron boron or cobalt samarium, even iron metal, you have to use high temperature metallurgical processes to make and fabricate these. Other advantages that they could be insulating. All magnets that you're familiar with are not insulating, they're conducting. They're all opaque in color. Could we make a transparent magnet? Could they be biocompatible? Technically high permeability. Now, one big advantage of them is maybe we can replace and improve upon rare earth-based magnetic materials with earth-abundant elements. And that, for most of the free world, is a problem because 97% of the rare earths are produced in China, which has export restrictions. And the US has identified these materials as critical risk materials. And so it would be nice to replace rare earth-based materials with earth-abundant elements. Now, the disadvantages is no one's ever made them. They're clearly going to be organic and low density with high equivalent weight. And low spin orbit coupling, which are technical points. But they could have advantages in emerging areas of spintronics, and as I will show you, magnonics, which is an area that we're pursuing that is on the cusp of being of interest to lots of people. And the Landé G value is another lower value that we have to live with to doing this. Now, someone has to tell me about time, because otherwise I will talk until the sun sets.
The idea, Joel, is something like 40, 45 minutes.
Okay, and with another half hour I have about?
A little less than that, but 20 minutes or so?
Yeah, okay.
25 minutes.
Okay, well, I'll aim for it. So the question is, can you make them? So many years ago, we reacted this compound decamethylferrocene with TCNQ, tetracyanoethylene. TCNQ, for now, it's now almost 50 years, has been used to make organic-based conducting materials. And we were interested in making a organic-based metal conducting material based on TCNQ. And we made this compound, which is a radical cation of oxidized iron 2 to iron 3, and the radical anion of TCNQ. And it turned out to be an alternating chain of cations and anions. Here, decamethylferrocenium ion, TCNQ radical anion, spins on both sides. And it totally was a failure with respect to conductivity. It's a poorly conducting material, not an organic-based metal. But when we studied the magnetic properties of it as part of our study and measured the susceptibility at 1,000 Gauss applied field, it rose up, had a maximum of about 2.5 Kelvin and dropped down towards 0. Indicative of an antiferromagnetic type of system, which is fine. Statistically, most things would be antiferromagnetic. But we also measured it at 2,000 Gauss applied field, And when you do it at 2000 Gauss applied field, it never reaches a maximum. It keeps rising. And we've taken it down to about 65 millikelvin, and it never goes down. And it acts as a ferromagnetic material. And this is, as I illustrated a few slides ago, typical of a metamagnet, where it's an antiferromagnetic ground state with a ferromagnetic excited state that you can reach, in this particular case, above a critical field of 1300 Ørsteds applied field. So below 1300 Ørsteds, it's an antiferromagnetic material. Above 1300 Ørsteds, it's a ferromagnetic-like material. So this suggested to us that perhaps we can stabilize a ferromagnetic ground state instead of an antiferromagnetic ground state. And chemistry-wise, we looked at TC and Q on the left over here. You can reduce it to the radical anion at 0.22 volts. And we decided that if you remove the benzene ring in the middle, you can make tetracyanoethylene over here, which almost at the same potential, a little harder, but not much harder, at 0.29 volts, reduce it to the radical anion. Now, the radical anion of TCNE is not as stable as that of TC and Q, but its volume is half as big as TC and Q, and each will have as radicals one spin. Therefore, the spin density of TCNE radical anion is twice that of TC and Q because it's one spin over half the volume. And so we decided that if it's smaller, we have more spin density to lead to stronger spin coupling. And being smaller, we can get closer to the next spin and maybe increase the spin coupling. And so we designed a system that we thought we could stabilize the ferromagnetic ground state. And so we targeted the synthesis of decamethylferrocene TCNE. Now, it turns out it's not as easy to make, but it's makeable. And I'm just going to simply tell you, reacting decamethylferrocene with TCNE oxidizes the iron 2 to iron 3 spin 1/2. TCNE forms the radical anion, a very similar structure for it. And in fact, I'm simply going to tell you point blankly, it magnetically orders as a ferromagnet at 4.8 Kelvin. Here is hysteresis loops within 1000 Gauss coercive field, which is half the width between these two features over here. And it is a bulk three-dimensional ferromagnet below 4.8 Kelvin. And here we have a slab of it on a piece of Teflon in a optical window, and we put in liquid helium. It gets cold. When it gets cold, it gets very magnetic. And when it gets magnetic, it's going to jump up to this cobalt samarium magnet, as you just saw. And when you let the helium boil away, it gets warm above TC and drops down. So this material over here is the first organic-based magnet. It's got a spin in the p orbital on the TCNE radical anion. We've done a lot of controlled experiments by replacing that anion with species that are different, with no spin on it, and it does not magnetically order. It's also the first magnet you can dissolve and remove the solvent and still be a magnet. And you do not have to use high temperature metallurgical processing to make it. The magnetization illustrated on top over here indicates that it is 37% more magnetic than iron metal is on an iron basis or a mole basis. So it's a very interesting magnetic material indicating you can make organic-based magnetic materials. I'm going to skip this slide and just simply tell you that we have replaced the iron with vanadium, the 5-membered ring, with a 6-membered ring. Now we use vanadium carbonyl. Reacting with TCNE, we end up making a material that's got vanadium and TCNE, no benzene or carbonyl, and it forms these black spots in solution. Those black spots in solution adhere to the ends of the magnetic stirring rod over here. And in fact, if you measure the magnetization versus temperature, this material, vanadium TCNE, now is a magnetically ordered material that orders at 400 Kelvin, 127 degrees centigrade, not 4.8 Kelvin, as I showed you on the previous slide. So now we have made a second example, and we've made more than 2 examples, of a magnetically ordered material. This material is a miserable material. It is amorphous. It's not stoichiometric, but it's magnetic every time you make it. It's also very air sensitive, so it will catch fire in the air as it's pyrophoric. But it does magnetically order at 127 degrees centigrade. And here is a powder sample of it in a vial. And you can see, as I showed you earlier, at room temperature in the air, it is magnetic, and you can pick it up just like you could pick up iron filings. So this is an interesting material. And oh my God, I thought I turned this off. Sorry for that intrusion. You can make films of this material by subliming vanadium carbonyl by chemical vapor deposition with TCNE in the gas phase, and the 2 vapors, vanadium carbonyl goes this way, TCNE goes that way. They interact and react in the middle and coat anything in the middle with vanadium TCNE magnet. And here's a piece of broken glass that's 99% by mass glass and less than 1% vanadium vanadium magnet, and it sticks to this cobalt samarium magnet. Here we've covered Teflon with the vanadium TCNE magnet, and you can see we caught a photograph of it flying through the air. It's being attracted to the cobalt samarium magnet. And here's a piece of iron aluminum that's coated with the vanadium magnet being attracted to this magnet over here. So it is a room temperature organic-based magnet that you can put on lots of materials. It's also a magnetic semiconductor. The conductivity for the best samples at room temperature is 10 to the minus 2 inverse ohm centimeters. Above 150 Kelvin, it's an activated Arrhenius behavior of about a half an electron volt. Below 150 Kelvin, it's modeled to be a 3D variable range hopping model with the T to the minus 4 dependence. And we have observed magnetoresistance in this material, suggesting spintronic applications for it. Now, there's a lot of work in the material science community of taking semiconductors and removing the diamagnetic metal ion, replacing it with, for example, manganese, to make dilute magnetic semiconductors with the goal of making a magnetic material at room temperature. And we do have a magnetic semiconductor that magnetically orders above room temperature, but it is not a dilute magnetic semiconductor. It's an intrinsic magnetic semiconductor. So it differentiates itself for people in that community. Now I was asked to talk about future things, and I'm going to talk a little bit about it right now before I go on with the rest of the talk with the time I have available. And we all know about electronics, and the electron is a charge carrier, and you have a piece of copper wire, and it moves from one end to the other end as the information character. We are migrating towards spintronics, where the information carrier is an electron, but only upspin or downspin, and spins in opposite direction are filtered out. And so we only have two types of carrier, up or down character. The world is moving a little bit slowly, but into the next generation called magnonics. Here, the magnon, a pure spin current flow with no particle movement, is the character. This is spin density fluctuations in a magnetically ordered material that can propagate as spin wave quanta or magnons. And so they move, and that's the information carrier, not an electron, not as a particle, but as a wave. And this has a few advantages. There's low heat dissipation, faster processing in the giga and terahertz region, higher fidelity, less information loss, propagation lengths fairly large, tunable materials by external magnetic fields, and in fact, transmission of electricity through an insulating material. Very unusual for common chemists like myself. And you can have multiple frequencies in a channel to do it. So this is the emerging area of magnonics. And just to give you a feeling for it, this is how it would propagate on the surface of a magnetic material to provide you information. The question is, can you do that? And the YIG or yttrium material, garnet, is the benchmark material for magnetic materials. YIG is, can only be made on GGG, a gadolinium garnet, gadolinium gallium garnet instead of an iron, yttrium iron garnet. And you make it epitaxially grow this. And this turns out to give you magnetic materials with low magnetic loss, a use called Gilbert dampening. It's not too important right now. And it has long spin diffusion, as we'll talk about. It has good spin mixing, so you can read it out using inverse Hall effect to do this. The problem with this is, in fact, you have to epitaxially grow YIG, and the only way to do it is on GGG, and even that is difficult. And it's expensive and challenging. So the question we raised is, can we make vanadium TCNE as a magnetic material? I just told you it's a magnet orders 127 degrees. And in fact, you can grow it on many substrates. And can we make an organic-based magnetic material? Well, I'm going to simply summarize a full talk on this by saying, yes, magnets can be generated on our vanadium TCNE film, and we can detect them by coherent magnets using ferromagnetic resonance. We can detect non-coherent magnets using the spin-Seebeck effect. And we can also detect them optically by Brillouin light scattering, and spin pumping, be detecting by the inverse spin Hall effect. Both can CW and pulsed lasers. And the Gilbert dampening is 2.2, which is very comparable to 2.1 times 10 to the minus 4 compared to YIG. And spin mixing coefficient is very respectable too. So in fact, we have demonstrated organic-based magnonics using our films of vanadium TCNE. The feasibility of this obviously has been generated. So I want to go and talk about one more material, actually 15 more materials, but we will just summarize it. If we do a little bit different chemistry now, instead of vanadium, we'll do manganese. We'll focus on manganese, take the diiodide and reacted with TCNE with a little acetonitrile in it, we can make a material that's got 2 TCNEs per manganese, and it magnetically orders at 69 Kelvin, a little higher if you do it with the iron compound. Structure of this has been determined by powder diffraction, and it has layers of TCNE bridging 4 manganese 2 sites. And these are layers that we will recognize as being ferrimagnets, which I'll come back to in a layer. And bridging the layers actually is the dimer of TCNE, octocyanobutane dianion, which is diamagnetic. So these magnetic layers are interconnected through these nitrogen, carbon, 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 nitrogen links to bridge this 3-dimensional network structure. And there's a little solvent in here, about 20% of the volume of the structure as solvent floating in and out. So the overall composition of this material of 2 TCNEs is in fact 1 TCNE and a half of the dimer of TCNE. If in fact we review the susceptibility versus temperature, we see a cusp in the data. If we look at the magnetization, we do not see any hysteresis. And in fact, this material is a bulk antiferromagnet, not a ferrimagnet, a bulk antiferromagnet. Now, I'm sure everybody's familiar with antiferromagnets. You have spin up and you have spin down, they couple. And the way you make this magnet is you look at the manganese has 5 spins up, it antiferromagnetically couples to the TCNE radical anion, which is 1 spin down. But each manganese has 4 TCNEs around it. So all 4 spins on those 4 TCNEs couple antiferromagnetically. Each TCNE has 4 manganese around it, and each of those couple antiferromagnetically. So all the manganese spins are up, all the TCNE spins are down. Spin 5½ antiferromagnetically couples with 1/2, leaves you with a planar 2-dimensional ferrimagnet net 4 spins. So we're looking normal to the layer compound here, and now we're going to rotate it edgewise. So it looks like this. And now we're going to map that spin onto the structure, and you can see this spin ferrimagnetic layer over here, and it will antiferromagnetically couple to this next ferrimagnetic layer over here through this nitrogen, carbon, 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 nitrogen linkage. This linkage provides enough antiferromagnetic coupling to lead to a bulk antiferromagnet. This is technically called an artificial or synthetic antiferromagnet because we couple antiferromagnetic ferrimagnetic layers. So these layers are not spins, but magnetic layers. And if we go back to Berg in 1996, he first demonstrated antiferromagnetic coupling between ferromagnetic layers via thin non-magnetic layers forms an artificial antiferromagnet. Now he did this by atomic deposition of metals, and this led to the discovery of GMR giant magneto-resistant based devices, which employ artificial or synthetic antiferromagnets, and led to the 2007 Nobel Prize by Ferd and Grunberg in this area. Our system, in fact, is manganese TCNE, which is a ferrimagnetic layer, coupled by half a dimer of TCNE, which is 8.77 angstroms, not even a nanometer, and represents a chemical way of multi-layers that you can make this type of system. Now, a moment ago, I showed you this cusp in the susceptibility or magnetization versus temperature. And now we're going to put some pressure on it. And we do that, we can see this data here goes from 0 to 5, and it's the same red dots here because I'm going to 1,000. And when I put pressure on it, you can see there's a quantitative change in the magnetization. So the magnetic ordering temperature up to 0.5 kilobar applied pressure does not change around 69 Kelvin. Above 0.5 kilobar, it actually goes lower and then rises as you increase the applied pressure. So it goes from an antiferromagnet at ambient pressure to a ferrimagnet at applied pressure above 0.5 kilobar. And if you reverse the pressure, remove it, it goes right back to becoming an antiferromagnet. So we can change the nature of the material by changing the pressure of this material. How much more time do I have?
5 minutes.
No more time? Everyone left?
No, people are still here. So
well, I'm going to go through one more compound, and we'll call it a day. We take the chemistry, instead of acetonitrile, put THF in there. We get a different IR spectra indicative of similar layered structure, but a different composition. And the magnetic ordering temperature suggests it's much higher than 69 Kelvin, closer to 169 Kelvin. And in this case, we see these layered compounds of mu4 TCNE radical anion bridging this layer here. But between the layer, instead of the diamagnetic C4 CN8, we have a radical anion that provides spin. And when it provides spin, it gives you strong magnetic coupling between the layer above and below, as opposed to weak magnetic coupling, as I showed you in the previous slide. And in this particular case, we have 1.5 TCNEs per manganese, a net plus 1/2 charge, and the counter ion, unknown at this time, turns out to be triiodide, half of which is floating in the structure. This material actually is now not an antiferromagnet, but a ferrimagnet that orders at 171 Kelvin and has hysteresis loops of the type you should expect to see for a bulk magnetic material. So just changing the solvent leads us to a material that's a bulk ferrimagnet, and the coupling you can recognize is going to be the same in the layer, but now the TCNE radical anion above and below also have a spin on it besides the 4 in the plane. And the one above and below couple antiferromagnetically with the manganese they're bonded to in the layers above and below with it. So all the spins throughout the solid are in the same direction. And so it's a net spin 5 halves, manganese up, spin 1/2 TCNE radical anion down, bulk 3-dimensional ferrimagnet. So I'm going to cut to the end now because we're running out of time. Just warn you, we have lots of other compounds. And simply point out that organic-based magnets can be made. They're added to our repertoire of new materials. They have interesting new magnetic properties for those studying magnets. They're clearly extend what molecular chemistry can lead us to in terms of new materials. And today we've got about 10 or 11 classes of magnetic materials. We talked about decamethylferrocene TCNE ordering at 4.8 Kelvin. We talked about vanadium TCNE ordering at 400 Kelvin. We talked about manganese TCNE half a C4 CN8 being an antiferromagnet ordering at 69 Kelvin. Talked about TCNE manganese with triiodide ordering at 171 Kelvin. but you can see that I was willing to talk about more compounds and still have many more besides those that I wasn't going to talk about to do that. So to summarize, organic-based magnets, we can make ferromagnets, ferrimagnets, metamagnets, antiferromagnets, artificial antiferromagnets, weak ferromagnets, which are canted antiferromagnets, spin glasses. We have demonstrated applications with spin waves, magnons. Other people have made chiromagnets and photomagnets. We have ordering temperatures up to 400 Kelvin, and we can control that. Large and small saturation and remnant magnetization, large and small coercive fields, demonstration for feasibility for magnetic shielding, spintronics, and magnetic applications. Other people around the world have studied lots of these materials, and there's lots of interesting for them and lots of opportunities for making, synthesis, modeling, experimental work, and we always need theory. I always like to show this particular slide. It was 105 years ago that Scott, then president of the Chemical Society in London, drew this as an illustration of cooperating materials, that particular case, manganese green salt. I've taken the liberty to add spin coupling as being important, but want to emphasize that the real importance is people coupling and people cooperating and collaborating and interacting, and on all the current basis of science, material science, biological science, is collaborations of people in different disciplines. And that's a very important aspect to move these important areas on the cusp of sciences in the forefront forward these days. The opportunities are immense for simply magnetic materials. We would like to make transparent and insulating magnets, flexible magnets, photomagnets, very hard, high coercivity magnets, and equally important are very soft, high permeable magnets used for AC motors and the like. Can we make a liquid magnet? That's an opportunity to think about. And clearly spintronic, magnetic, and spin transistor materials and the all organic motor are clearly opportunities in the future that might come out of organic-based magnetic materials. And here's the group that we have in Utah working in the area, and we collaborate with for worldwide to do that. And we like to continue that. And I just give you a picture of our home, which you can't see. Where I live is now way down in the mountains here, but we are in the rock. We have lots of snow where we live. Not today, but next door in Colorado got 70 centimeters over the weekend. That's it for me. Any questions that might arise?
Can I ask a question?
Yes, go ahead, Chaim.
Someone talking? I hear no.
I'm asking about magnons. Can you say a
now
little
I
bit
hear
more?
it. It's my mistake. Sorry?
Can you say a little bit more on the magnons? What kind of lifetimes or wavelengths, energies do you excite them with circular polarization? What do you do with those?
We do it with circular polarized light, and I don't know, I don't recall the lifetimes. It's a big collaboration with physics, and I'm not the physics expert in the area. I'm the synthetic chemist that makes them. The lifetimes, I don't know that we've studied the actual lifetimes. It's the coherence length.
Mm-hmm.
If I can go back to the slide that summarizes the data for it. Over here, no, I'm sorry. Yeah, I don't have a lifetime information.
Mm-hmm.
but it does have a small dampening effect, which indicates there's some reasonable coherence length in there. Sorry, I can't answer that anymore.
Okay. Yeah.
Can I ask a question?
You can. Yeah, I'm sorry I turned the sound off when I missed some. I presume there was questions during the talk. This is new to me. Anyway, continue with the questions.
Yes, Chef.
Joel, I have two questions. One is a trivial one. Is there any interest in the industry in this work or not?
We have not found any industrial collaborators, although we're talking with someone to perhaps support some of our work. But the fact of the matter is, it's very initial preliminary work with that we don't foresee a device with less than 5 to 8 years out of it. And so we just really need to understand the very basics of these things.
And the second question, you did not allude any, or you did not speak about the crystallinity of these materials. Are they amorphous, completely amorphous, or they are semi?
The vanadium TCNE materials are totally amorphous. All the other magnetic materials that we have made, some that I talked about, some I didn't talk about, are crystalline and diffract. Some are big enough for single crystals, some are not. We can only study them by powder diffraction, but they do diffract. This particular, the vanadium one, do not have crystalline order.
So do you see any relationship between the domain size and the crystallinity?
No, we've not studied domain size and crystallinity, but it's well known that if you take nickel metal, which is a crystalline material and magnetically ordered as a ferromagnet, you can melt it and quench cool it into liquid nitrogen and you'll get amorphous nickel, and that amorphous nickel will also be a ferromagnet. It will not be as magnetic as the crystalline material, but in fact will magnetically order, and the ordering critical temperature will be lower, but it will still magnetically order, suggesting magnetic domains are sufficient to support magnetic ordering, but not as good as if you could make a crystalline material. And we've always been interested in trying to make the crystalline material, the vanadium TCNE, arguing it should be better, but we have not achieved that.
Joel,
I had a question. Oh, sorry. Okay. Yeah, thanks. I really enjoyed this talk. I'm wondering about what you showed, the effects of pressure. With the material that you demonstrate that on, was it one of these ones with a proper crystalline structure that you could see the effect of pressure along a particular crystalline direction, or this was just a pressure cell that evoked pressure?
Well, the answer is we did it in a pressure cell, but and it is crystalline, but it's not easy for us to get crystal powder diffraction data as a function of pressure. We have done that on a few occasions by collaboration, and we would really like to do this and study the phenomenon under pressure to see what happens. There's clearly got to be you would expect under pressure that the antiferromagnetic ordering temperature should become greater, but there's got to be a structural change to go from an antiferromagnet to a ferrimagnet, and we'd like to see that, and we just have not been able to study that. But in principle, you should be able to study the powder diffraction of it and hopefully refine the data to collect that data, but we've not been able to do so in this compound.
Mm-hmm.
Can I ask a question?
Go ahead.
Yep, certainly. I don't know who it is, but that's fine.
I'm David Bergman.
Please ask away. Okay.
Many of the materials you described, in fact, most of them are based on TCNE.
Correct.
Is there some other organic molecule that you could use to find similar materials?
Yes, the answer is yes. You can make purely organic materials with carbon and hydrogen and nitrogen. Nitroxides, for example. Some nitroxides will magnetically order. Paranitronil nitroxide orders at 0.6 Kelvin. So it's got nitrogen, oxygen, carbon, and hydrogen, no transition metals in it. And there are many other nitroxides that will order, the highest of which is 2.55 Kelvin. We, in fact, have made lithium TCNE, not to get away from TCNE, which does not even have oxygen in it. And lithium is lower atomic mass than even carbon. And it magnetically orders as a weak ferromagnet at 21 Kelvin. And you can make other examples of it to do that. And we can make other organic radicals, hexacyanobutadiene or TCNQ, radical anions, and make magnets out of it. The fact of the matter is the TCNE analogs of any of the other ones, they're simply more plentiful and higher ordering temperatures. It works better. But there are other examples we and other people have made.
Joel, I had one question when you mentioned at the end about the theory. I'm an experimentalist, but it looks to me like a very interesting, topic for a software that would make all kind of combinatorial studies to try to find out molecules that exhibit this phenomena. Is there anything out there that does this? Like, I mean, in DFT, there's Espresso, I don't know, they have all their softwares going on, but for this, I've never heard anything.
I'm unaware of anything too, because now you got to predict the onset of three-dimensional ordering based on a structure, and we never have enough structural information. It's very rare we have ordering temperature, structure below the ordering temperature, and enough information. I mean, there's so many couplings going on that are competing. Generally, some are anti-ferromagnetic, some are, I didn't show this, I rushed through here. But the coupling for the TCNE decamethylferrocene is strongly coupling within the chain and some weak anti-ferromagnetic coupling between the chains. And the net coupling is ferromagnetic and it magnetically orders at 4.8 Kelvin. So the answer to that, I think it is a computational challenge, which anybody is, I don't recommend it. I think there are more tractable problems than this.
I see.
So I just play synthetic chemist and touchy-feely intuition of what compounds together might give you couplings that may be strong enough. And all you can predict is the couplings, I think, and whether in fact they will magnetically order and form domains is well beyond my level of prediction, except for good luck.
Okay. Other questions? Well, if there are not other questions, I want to thank one more time Professor Joel Miller. Fantastic talk, very fascinating area. I didn't know anything about it, and now it's very, very inspiring. And to all the attendees, thank you for attending. Please let people
Thank you for inviting me. It was a fun, this is my first webinar. I have to learn the methodology a little better to be a little quicker on it, but that's okay.
I think this is a little bit here to stay. And I'll tell you one thing, we learned one thing at IVS, that it opens the boundary for having people from other countries to join a local Israeli conference. And
sure. there's a lot of advantages of it.
Very, very interesting way that we can really shorten the boundaries between people,
right.
Scientists. Yeah. So Joel, thank you very much again. Thank you everybody. And there is the next one, if I'm not mistaken, is Professor John Hart from MIT, who will be talking, and we have to just to advertise the date and so on. So keep posted.
Okay.
Thank you.
Well,
bye, Joel.
Thank you very much. Shalom. Be well. Stay healthy.
Shalom, shalom, Joel.
Shalom, shalom.
Bye. Bye. Thank you.